Hello and welcome to my channel. My name is Milos, and in today's tutorial I will show you how you can create some awesome 2D and 3D land cover maps using the ESA global land cover datasets. Welcome back to R, where we first of all install and then load the libraries that we need. The easiest way to do that is to first of all install package pacman, which will do the rest for you. So I already have the package pacman, so I'm gonna go ahead and take pload function from this package, which is going to help me exactly do what I need. So I'm going to actually use pacman pload, install the packages I need, and then load them directly into R. The first package I need is RGeoBoundaries, which is going to help me fetch the polygons of the national boundaries of Belgium. You can also use it for any other country, also substate region. You just need to provide the ISO3 code for the country of interest. The second package is RStack, which is going to help us communicate with the planetary computer by Microsoft and then get the ESA world cover dataset for 2021. The next package we're going to be using is the asset package, since we will be a bit also working with the polygons. And then more importantly, we'll be also using Terra package for working with raster files, because in today's tutorial, we're going to be working with land cover, which is a raster file. Then apart from this, we definitely want the Tidyverse umbrella package, which is going to give us access to ggplot2, but also to dplyr, tidyr, other data wrangling libraries. Then after this, what we definitely need is the elevator package, which gets us an easy access to the AWS tiles for the elevation, because we'll be adding the elevation in building our also 3D land cover map. And then I want to add also here two additional libraries, which are going to be very, very useful for us. One is ggturn, which we used before, and this is going to help us get the colors from the raster file, so the actual ESA colors. And then the second one is ggspatial, which allows us to get the scale bar and also the north arrow. Okay, before we proceed, these are the libraries and their versions that I will be using in today's tutorial. Our next step is to define our area of interest and fetch the polygons for that area. So in today's tutorial, as I mentioned before, we'll be mapping the land cover of Belgium. So to get this one, we actually need to use the RGeoBoundaries package, which has a very convenient function, which is called GADMB. Now, what is very cool about this function is that allows you these are actually 6 functions. So it allows you to have different levels. The 0 level, which we'll be using, is the state, the national level, but then you can also have sub-state levels, and they can go very granular. So this is also the way for you to filter different sub-state levels. So let's say you're just interested in a region of a country. Now, in this tutorial, I'm just going to show you for a bit smaller country like Belgium, how you can get the data and then how then you can plot it. The only thing now that you need to provide here is the ISO3 code. For Belgium, that is BEL, so B-E-L. For some other country, it could be some other ISO3 code. Feel free to Google the appropriate ISO3 code for your own use case. And then the last step in this section is to get the bounding box of Belgium, because we will be using that to also fetch then the land cover dataset. So let's actually find this one. Let's call it country bbox, and then here is where we're going to be using the asset package to create this bounding box with the help of this st_bbox function. So over here, we just need to pass then our country asset object. In this step, I will show you how we can actually query the ESA world cover dataset from the Microsoft Planetary computer using this API address over here. And actually this step and some other steps, including step number 5, so 3 to 5, are coming from one of my previous tutorials where I also show you how you can get the data. So you can also go and check out that video, which is also pretty useful. Now, in this case, what we will be using is, first of all, creating a query that is going to help us fetch the appropriate data set from the Microsoft Planetary computer. And I'm going to call this MS query, MS like a shorthand for Microsoft. This is where we're going to be using this RStack, and stack is the function that we need. Now we're going to go and simply copy this link, and we need to wrap it around this double quotation mark. So essentially turn it into a string. Now, the second thing we need to do is get all the possible collections, because Microsoft Planetary Computer hosts so many data sets, but we need only the ESA world cover. Now, to get the list of all the collections, what you can do is, again, use this query that we just wrote. So this MS query, put it into a pipe, and then from RStack, you can use a very convenient function, which is called collections. So this is going to give you the list. And then the last step you need to do, again, use this RStack and just send your request so that you get all those lists. Now, if you're interested in the list here, you can print the entire list. And the entire list, if I'm not mistaken, has actually 123 collections. And then among them, you can find the ESA world cover. You can find some other ones. In our case, we're just interested in ESA world cover. And the ESA world cover, without going into the collections, as we did it in the previous tutorial, we simply know that this is actually the name of this dataset. So it's ESA-world cover. And we can immediately define this as our collections, right? So this is the one that we are interested in. Now, the question is, how do we actually get the data? So we now wrote this nice query. We have all the info we need. This comes through another RStack, actually function, which is called stack search. Now, this is gonna get for us this specific query. It's gonna get for us specifically about the ESA world cover, what we need to know. And then once we actually have that, we can then pass it to the Microsoft Planetary Computer and get the specific tiles for our area of interest. So this is how we can do that. So again, we can call RStack, and then from RStack, we need a function which is called stack search. All right, stack search accepts several arguments. First is the query. So for the query, we simply need to pass here the link to that API. Now, the second thing is defining the collections you want to get. So you can get actually more than one collection, but in our case, we're just going to get the collections that we already defined, and that is the ESA world cover dataset. After you define the query, after you define your collections, then you need to define here a datetime. Now, this one is actually pretty specific because the ESA world cover dataset that we want to fetch, there are two. There is one for 2020 and there is one for 2021. We want the most recent one, which is 2021. And that's why we're going to be actually putting here this date string. So it's not just enough that you put here a date, it needs to be accompanied also with a time. And the time needs to accompany the beginning of 2021 until the last day and the last minute and second of 2021 as well. So 31st of December. This is simply needed to capture the entire year, even though this data set is not really time series because it has for 2021, but it doesn't have for, let's say, specific months or quarters of 2021. Now, once we have this, this is where we actually put what is the bounding box here. This is where we can put our, for example, country bounding box, or if you're working with some regions, you can also put here your regional bounding box. And actually, once we have this, the only thing we need to do is write here a pipe, and then again, use from RStack this function, which is called get requests, which is then going to be used to send requests to the API, and then we can get back the information about this data set. Now that we have this query, the next thing is to sign in for free to the Microsoft Planetary Computer and from R, so we don't need to leave our studio. And after that, we can download finally those land cover tiles, which are going to be downloaded locally to our drive. So let's start off, first of all, by signing to the Microsoft Planetary Computer. Okay, so to sign to the Microsoft Planetary Computer, we need to actually create an object, which is going to be our sign in. And then from RStack, what we want to use here is a function which is called items sign in. So this item sign is a way to actually sign in here. And what we can then say here is that we want. Then after that, there is another function which is gonna actually directly then connect to this planetary computer, and it's called Sign Planetary Computer. Okay, so now we are ready to actually send finally this to the Microsoft Planetary Computer and to download. And to do that, we first of all need to define where we're going to be, downloading to all those files. So I'm simply going to download this to my working directory. You can also maybe download it to your temporary directory if you wish. And after that, we are going to go for the final function from the RStack, which is called assets download. So to this one, we need to provide this query sign in. So it's important that you take this sign in query, because this one also has, this part which allows you to sign into the planetary computer. That's the first one. The second one is going to be asset names. For this one, you want to choose map. Then you need to choose the output dir or directory. And here we can go for this main directory, which we defined. And then finally, if you already have these files, maybe, then you can simply overwrite them if you just want to download again. And this should take usually around a minute, depending, of course, on the current number of queries to the Microsoft Planetary Computer. But in general, it should not take more than several minutes to get the data. Now, this was now downloaded, and what we need to do next is create a path to the directory where these files were downloaded, and then we want to load them into R. And I'm going to show you now how you can do that, including cropping actually the data to just simply the polygons of your region or country or some other entity. So let's start off by defining the elements of this path to the folder. The first one is, of course, the version we are going to be calling here. So the version is v2, or the second version of this data set. Then the year is 2021. Just notice how I'm actually defining everything as a string, because I'm going to be building now path to this directory with the use. So that is gluing together these elements, and our main going to help us be able to access all those files that we downloaded to our folder. So we can use file path from base R, and then to this file path, what we can do then add, so main directory. So this is the one that we defined to download the data. Then collections is the next one. So this is the second level there. Then we have the version, which we also defined, followed by year, and finally asset name. So then we can actually use this file path, and then we can enlist all the raster files that we have there. How do we do that? Well, first of all, let's define this raster files, and then use list files from base R, which is gonna actually perform this for us. So it's simply gonna grab based on this data there that we put here. And also, very importantly, you want to actually grab the full names. Now, okay, once actually we run this, and I go over here and take this one and open, you can see that the engine has downloaded 30 tiles to our local machine. So the next thing we want to do is we want to import all of these tiles, but we want to glue them all together. The easiest and the most efficient way that I found using Terra would be using the virtual raster layer. So that would be the function VRT. Now, we can simply create a new one. It's going to be called land cover raster. And then from Terra, we can use, as I said, VRT. So essentially, VRT is very similar to Terra Mosaic and Terra Merge, but actually it's much faster because it creates, as you can see, virtual raster data set from a collection of these different tiles. So it's extremely fast. It does things within a second. So the thing we just need to do here is the following. We just need to provide these raster files, and then we're actually going to have this information. When you inspect this raster file, you will notice that the dimensions are huge, and this is because we simply glued together all those tiles. You will also notice several other things. Their resolution. So this data set, as you know, or you may not know, is a 10 meters resolution. So this is also reflected here. It also shows us the extent used in WGS 84 coordinates reference system. It has a color table. So from this color table, we will be getting now colors in the next step. And this is simply a generic name, which is inherited from the Microsoft planetary computer. Before we actually fetch the colors, the only thing that is now left is to crop this raster file and then have only the land cover raster file for the extent of Belgium. So basically get rid of anything that is outside of the boundaries of Belgium. So for that, we can actually use, so we can again use country land cover. I would say we can call it that way. And then from Terra, we can use crop. And then within Terra crop, what we need to pass, first of all, this land cover dataset. The second, we need to pass the SF object, which is country SF. And then we need to say that we want to only take what is inside of the Belgian boundaries, and everything else will be declared missing. And this is what this mask equals true is for. Then once you actually perform this, you can go ahead and do a quick and dirty plotting of this data set, this country land cover, like this. And you should be able to see the land cover map of Belgium, though without the legend, but you can see coordinates reference system and the colors here, which we'll be grabbing in the next step. We'll be using the method for fetching the original colors from one of our previous tutorials on mapping 3D land cover from another data set. Now, here is what we're going to do. First of all, we're going to create a raster color table. And over here, what we're going to be doing is we're going to be, first of all, putting together the color table of all these colors from our raster file. So this comes as a list, so we actually need to create it as a data frame. And this is why here I'm using this do call and calling data frame function. Because this Terra call tab is essentially going to give you a list of all the colors. So the colors should come from this country land cover. Now this comes in the form of RGB, but we need a hex code to work in R. So what we're going to do here in the next thing is we're going to be using this ggturn package. And from ggturn, we'll be using RGB to hex function. So as you know, RGB stands for red, green, and blue. And we also here need to define red, green, and blue. And for red, it's R, for green, it's G, and for blue, it's P. So for the red, we essentially need from this raster color table that we got here, we need to get the second element. So because in this data frame, we essentially have 3 columns. The second one is are the values for the red. For the green, it's the thirds. And then for the blue, it's the fourth column. So I'm simply like copying and pasting here because essentially the only thing I'm changing here is this number. Then if you quickly inspect these hex codes, you will see that here we have 255 hex code values. Now, this comes maybe at a surprise because we know that the ESA World Cover dataset has 11 values. So essentially, we do also have 11 values here, but they're buried among all these zeros, which essentially are values for black color or simply missing values. So what we're going to do is next, we're going to filter this vector and we're going to take only those hex code values that do not include, these zeros. So only those that are something else. And here's how we can do that. So we can simply create a new object and call it calls. Then we're going to take this hex code vector. And then we're going to say that we're going to filter out. And this is why I have this exclamation mark here. So this exclamation mark helps me to kind of filter out things. We're going to be kind of filtering out everything that is equal to, and then values that have actually these 6 zeros. So this is essentially all the black colors. So this leaves us actually with 11 values, and these are exactly the values from the ESA World Cover for its classes. And the very, very last step is to, before we move on, get rid of any missing values in our raster file before we proceed with our analysis. So we can simply use this NA omit, and we are doing this exactly because since we got rid of the black values means we don't really show any missing values. And for that purpose, we only need those values which are not missing in our raster file. As you remember, our raster file is really huge and we are only using the data for Belgium. Nevertheless, there is a very easy way to resample your dataset. And for that purpose, we'll be using the elevation data with a low resolution and then resample our land cover dataset with this one. So here's what we can do. We can use elevator package. An elevator package has a function which is allow us to get elevation data. So we can use get elef raster. And over here, we need to specify what are the locations for which we are getting this data. Of course, we're doing this for this country SF. Then we need to define what is the level of granularity of the data. So the higher the number, the more granularity, because Belgium is a small country, territorially speaking, we can use a pretty higher number. You should readjust this one in your case. So you do want to have a raster that does not have probably more than, let's say, 4,000 pixels in either its width or height. And then finally, we need here to provide a clip. So how are we going to clip this? We're going to, of course, clip using the polygons. So that would be these locations. And then before anything else, elevator usually returns, or elevator actually returns in the raster format, but we want a spat raster so that we can also work here with Terra. And then we can go ahead and resample our land cover dataset using this digital elevation model. Before we do that, I would like to actually define a specific projection for Belgium, and I will be using the coordinates reference system for European countries. And this is actually that one. So it's EPSG 468. And of course, you need to define it here as a string. If you're curious, what is the coordinate reference system recommended one for your country of interest, you can go to epsg.io. And over there, you can then search for your country of interest and then see, usually it's one of the top results that is the most recent coordinates reference system. Going back to our case, we can finally go ahead and resample our land cover dataset. And we can use, like in some of the previous tutorials, resample function, a very convenient one from Terra. Over here, we need to define, first of all, what is that we want to resample. And as we said, we want to resample our country land cover dataset. So that's the first one. The second one is the Y argument. What are you going to use to resample? We're going to be using here digital elevation model, this one. Now, what is very important is, at this stage, it's very important if you're maybe working with some other digital elevation model to keep the coordinates reference system for your X and Y to be the same. So in our case, this is true. It's WGS84, so we don't need to worry about it. But if you don't work with the same coordinates reference system for both objects, it might happen that I will throw an error. So it's something just to think about it. And then the final one is, how do you want to resample the actual cell values? Now here, what we're working with are discrete values, right? Land cover classes are discrete. So we cannot use the default one, which is bilinear, which is kind of a fit for continuous values. We need to use this near neighbor method so that it actually then help us, get proper discrete values and not get the decimals. And then what we also need to want to do here is, of course, reproject then this resampled land cover dataset. And then we can reproject to this proj. Now, what is very important is you also need to here specify this same method near, because if you don't do that, then after running this and after reprojecting your raster, it essentially, the values which were discrete up to this point are now going to become continuous unless you put that you also want to resample using this nearest neighbor method. In this part, we're going to be slowly preparing for mapping and setting up all the necessary details. And one of them is definitely the theme for our map, which I like to call theme for the win. So what I usually do is I create here a function. And within this function, then I define, okay, what are going to be the main components of my theme? The first one is going to be that I want to have a minimal theme. And then from there on, I can actually customize the theme using just the theme argument. Now, one thing that I like to turn off or like to remove from my theme are axis lines. So I just like to put the element blank. If you, however, like to have the axis lines, you can also keep them. The same goes for the X title. So basically that would be the longitude, the horizontal one. I also like to remove it. And the same goes also for the Y-axis title. So for the latitude, I also like to remove that. The same goes for the axis labels, and those are actually the coordinate numbers, the degree numbers. I also like to remove those. So this would be axis text X and axis text Y. Again, if you want to keep those, you can simply remove these two lines here. Okay, now the rest, what I like to do is also remove those grids around my plot. So panel grid major, this also is going to be removed. And the same goes also for the panel grid minor. So that one is also going to go out. Okay, and then also one more thing is removing the plot background itself. So that is going to be what is behind the plot. That one is also going to be blank. And the same also goes for the legends background, because we don't want some extra shadows as we prepare for rendering this into a 3D object around our legend. Okay, once we're done with this kind of a boring part, turning off stuff, we can then go and really customize some of the things. And one of the things I would really like to customize here is the legend position. So a legend position essentially defines where the legend is going to be. And you know that we're going to have a legend with 11 elements, or actually it's going to be the number of classes depending on how many of those classes are available for the land cover of Belgium. But anyways, what I would like to do is I would like to, since we know how Belgium actually looks like when we did that quick and dirty map, we know there is some place in the lower left corner. So what I want to actually do here, I want to place my legend there. So here I'm going to define two values. One is X. So I want it to be kind of at the beginning. And because I want it in the lower left corner, I also want the Y value, which is for the height. I also want that to be low. So this is actually going to give me this sweet spot. And then I can go ahead and, I can define some other things related to the legends. For example, I can define the legend title and the legend text. Now, when it comes to legend title, this is actually text. And we need to tell, R that legend title is element, sorry, not ternary, but text, so element text. Because otherwise it's not going to know how to treat this one. So over here, what we can do is we can define, for example, size of our text. Let, for example, be 11 pixels. And we can also define color. For example, we can opt for charcoal gray in this case. And then what we did for the legend title, we can also do for the legend text. The only thing I'm going to do here is, decrease the size of the legend text. And of course, here I do need to rename this because I don't want it to be legend title. And I can, for example, choose 10 pixels over here. And once we do that, we can then also customize, for example, plot title. We can also add plot title to make it also look better. So I'm going to actually go ahead and use here plot title. Now, plot title should be more visible than just 11 pixels. So we should opt for something like, let's say, I don't know, 20 pixels. You can change also the color here. I'm going to keep it the same. I would like the title to be in the middle. So I'm going to use here 0.5 for the horizontal justification, or this adjust. And for the vertical justification, so where it's going to go up and down, I'm going to go for a bit of a negative value. Negative value is actually going to move the plot title closer to our map. We can also have, apart from the title, also plot caption. So in the caption, for example, we can put our source. We can also put our credentials as well. And over here, what I like to do is make caption even smaller than the legend text. We can keep it maybe at also charcoal gray or something like that. Also, I would like it to be horizontally justified, but I would like to push it a bit towards the map. So that's why this vertical justification should be positive. All right, and then last but not least, I would also like to define here plot margins. This comes very in handy if you want to shrink that white space or like that extra space around your map or around your graph. So over here, what we need to do is we need to define actually units. First of all, units, and then provide a list of those, sites and what we want to do with them. So the easiest way to shrink is simply define 0 for each of the 4 sides, for the top side, for the right-hand side as well, for the left-hand side. You also wanted to put to 0, and then bottom-hand side as well, 0. If you want to shrink it even more, you can turn this to negative values. But essentially, what is very important is that here we also define, are we going to use centimeters, inches, or for example, lines like I'm doing here. The next step is to prepare the data for plotting. That means we need to have the appropriate labels, and we need to have the appropriate numerical values from that ESA World Cover codebook. So what I actually did here, and what I want to show you, is how you can create easily those values. So if you remember, if you go back to this ESA codebook, which are also provided in the description box below, the link to it, you will see that there are values from 10 to 100, and they are divided by 10. So you have 10, 20, 30, 40, 50, 60, 70, 80, 90, and then 100. And then you have also a value of 95. So I'm going to show you here how you can create those values, how you can append them as well. So what you need to do, first of all, you need to create a sequence. Sequence is going to go from 10 to 100, and it's going to be by 10. And then what you want to do in the next step is to simply append this vector. And then you want to append it with 95. So you want to have values, you want to have 95, and then you want to have after the 9th element. All right? So essentially, what you need to see here once you run this is the following. You need to see these values. So from 10 to 100 with 95 inclusive. And then we also need labels. What I did was simply copy and paste from that codebook the values here. So these are all the 11 values. And of course, I declare them as strings. Now what I'm going to do next is I'm going to put them into a vector, into a list here. And once we have that, the very last thing is to actually build our codebook. The reason why we are building it as the data frame is that we can then easily use it to filter out all those land cover classes that are not in our Belgium data. Because in the Belgian data, we are not going to have all those 11. Some of them are going to be missing, and this method is going to help us determine that. The good thing about this method is going to help you in your specific use case also remove some land covers if they're not, for example, used. All right, so here's what we need here. We need several things. We need values. So values are going to be coming from this values data frame or actually a vector that we define. Then we're going to have labels also from this labels vector. And then finally, we're going to also here include colors, which we defined in one of the previous steps. So then actually, you're going to have a data frame with 3 columns, values, labels, and then colors. And this is going to have 11 rows. Each of these have 11 rows. Okay, so once we actually have that, we can go ahead and turn our land cover raster into a data frame. And we can call this one country land cover resampled DF. And then we can use as data frame. And then over here, we can pass our object, which is simply the same name, but just without this underscore DF. And then we want to turn this into every pixel needs to have its coordinates and the value for that pixel. So that's why we're saying here xy equals true. And finally, we're also going to remove any of the missing values that might be here. So once you actually do this, you will get 3 columns, X column, Y column, and then that value column, in our case, meaning, what is the land cover class. Now you want to make sure that that 3rd column, that the name for it is in a specific format. And in our case, what we want to do is we're going to rename this one and we're going to simply call it values. The reason why I'm going to call it values here is that in this data frame, we also have column which is called values. And values in the codebook here and values in this newly created data frame from the raster file essentially have the same values. So what I'm going to do is I'm going to use this codebook and I'm going to filter out values based on our specific land cover data frame here, and keep only those land cover classes that are in our raster and discard the rest. So this is how we can actually we can do it after this. So the first thing that you want to do, make sure that your codebook values and your this one country land cover sample df values column are of the same type. So in our case, this one is already the integer type, but this one in the codebook is not. So what I'm going to do is I'm going to here transform it from a character to a numeric one. So I'm just going to pass it like this. Okay. The reason why we're doing this is that in this step now, what we're going to do is we're going to join this codebook and this raster turned into a data frame to be able to actually filter and keep only those land cover classes that we have in our raster. So in doing so, we can create a new object, which is going to be country land cover df. And then over here, from dplyr, we can use an option which is called left join. So this is going to help us keep only those that are available in our raster file. So over here, we can then pass this country land cover sample df. So this is the one that we join on the left side. On the right side, we join this codebook that we define. And then for merging together, we can use by these values. And because land cover classes are discrete, we also want to make sure that we turn them now within this new object into also a factor. So I'm just gonna go ahead and create here, or not create, but simply I'm going to declare this as a factor. And this is then going to have all those different levels. Now, before we jump into creating the map in the next step, what I want to do here is take only those labs or labels and only those colors that correspond to the existing land cover classes. So what we can do here is from that existing labels object, we're going to go ahead and filter that labels, and we're going to say only for those that are appearing and that are unique within this country land cover df from the, of course, labels from the labels column. That's the first thing that we're going to do. The second thing that we're going to do the same but for the colors. And here we can just simply define them as palette or a shorthand for palettes. And over here, instead of labels, we're going to just put, so we will be filtering that calls filter over here. And then over here, instead of labels, also you want to take the calls column from this country land cover data frame. All right, we are finally ready to create our land cover map using a ggplot2. The first thing we will do is, of course, call ggplot2 using its ggplot function. And then we're going to be adding our one and only layer, which is a raster layer, of course, turned into a data frame. So over here, we actually have the data. The data is the last one that we created, so country land cover df. And then for the main aesthetics, we need to define actually three components. That's x, or longitude, y, latitude, and then of course how we're gonna fill those pixel values. We're gonna fill them using values. Now we also want to make sure we again declare these values as a factor, because remember, land cover classes denoted with these values are essentially discrete values, and we want to make sure that we also capture that. Okay. So this was one and only. The other thing we want to do is we want to here now, of course, define some of the stuff that we have. One of them is, of course, we want to define the colors that are going to be used, in our map. So that means we can first of all define land cover class. This is going to be the title or our legend. Then for the values, we can use that palettes object that we previously created. And then for the labels, we can just use labs that we also previously defined. So this is then going to give us only the values that exist in our data and only labels that exist in our data, and they're corresponding to the levels of this values factor. Once we do this, we can then go ahead and customize the legend. Customizing legend in ggplot2 is done using guides argument. So our main static is fill, and that is the one that's going to change. So this one is the one that we need to also define here. And then within this guide legends function, then you need to define, how you want this to look like. So I would actually like, first of all, our legend to be vertical. And then second, I also want to define the bar width of it, and I also want to define the bar height. So the way we define this is using simply units. And for example, I want to say that I want to have 5 millimeters, so that's a half centimeter. And I would like to have actually both our bar width and our bar height to be the same. So essentially, we get the same values there. So once we actually have this, then we can use this new ggspatial package here to add, first of all, annotation scale, and then to annotate also the north arrow. Let's start off with the annotation scale. So the annotation scale, you can first of all define where you want to have it. So I would actually probably like it to be in the bottom lower, or the lower left corner, so that would be BL, meaning bottom left. Then I would also like to decrease a bit the width. So I don't want this scale to be longer, because remember, our legend is also going to be in that same corner. So I don't want the scale to go over our legend. Okay, we can also define some other things. We can also define how much this is going to be away or close to the edge. So this is pad underscore X and pad underscore Y. So over here, you define again in centimeters or inches, whatever works for you. So I would like this to be probably around half a centimeter away from the edge. So we don't run the risk of actually the scale going over the board. So we don't really see, what's going on. So this is how you actually define this. So this is the annotation scale. There are, of course, some other things. You can check them out, what this annotation scale does for you. But the way we did this, we can also add, because it's from the same package, the ggspatial, we can add, of course, the annotation, and then not scale, but north arrow. So this one, we actually want to put in a different place. We want to put it in the upper right corner. So that would be TR, meaning top right. Then one thing is, we are not really concerned about the width, because north arrow is like relatively small, but we want to choose here a style. So how this is going to be done. And there is one here that I like to use, which is north arrow fancy orienting. But you can also choose some other styles. Like, you can literally see what works for you. And then I'm going to keep this 0.5 and 0.5 here. Now, one thing that I want to do is, I think I want to a bit increase the space here from the x-axis for my annotation scale. So this is the only thing that I'm going to change. And once we are done with adding this stuff, I think the remaining thing is just like adding some more, additional things here. So one of them is, of course, we want everything to be in this coordinates projection that we already chose. We also want to add some of the labels here. So one of them is, for example, we want to have a title. So for the title, we can, for example, do land cover, and then in uppercase letters, we can write Belgium. Then another thing we want probably to have is caption. So for example, I don't know, for this one, I like to usually put, what is my, who created this, so I usually put my name. And then I use this one to just kind of a break, create a new row. And then I add here, of course, the data source, so the link to it. And then the last one is, I would like to add that theme that we created. But before I do that, I actually want to make here an amendment. So I want to go actually back to that step where we created this theme, and that would be step 8. And while we are here, actually, one of the things that I changed in the meantime is this plot background. So I realized, actually, because we are also going to be using rayshader to render this, if I leave it as a blank element, it's actually going to be, the background is going to be just blank. So I actually decided to add this element rect, because this is a rectangle, and then to have it filled in white. And then just for the colors of the border of this plot background, I'm just gonna keep it as missing. All right, so once you actually now know that I changed actually this part, which is plot background, and I change it to this, we can then go back to our plots over here, or code, and simply here at the end, add our theme for the win. And here it is, ladies and gentlemen, our 2D land cover map of Belgium using ESA world cover data. Apart from the map with these vivid colors, you can see that we have a legend which clearly defines only those land cover classes that exist on our map. Below that one, you can see the scale. And then in the upper right corner, you can also see the north arrow. Apart from that, there is also a nicely aligned title, so it doesn't go over the map. And there is also a caption, which is at the bottom of the map, and it's also clearly visible. Do you want to create custom land cover or forest maps in just a few clicks? No coding, no dragging, no hustle? Meet Maya Maps. With Maya Maps, you skip the manual work and repetitive data tasks. It's a powerful web tool that lets you pick from curated datasets using proven, standardized scripts to get reliable, repeatable results. That means you don't need to write a single line of code. Plus, with LLM integration, you'll get easy to understand, text-based interpretations of your results, making analysis a breeze. Imagine getting beautiful maps, complete with legends, tailored to your area of interest, all in a shareable PDF format. Want even more? Share online links with interactive time series maps, charts, and insights for a deeper dive. Creating your map is simple. Head to maya-maps.com and click Order Maps. Select your area. Got a GeoJSON file? Upload it in File Upload mode. Don't have one? Use Draw Shape mode to sketch your area on the map. Click Request Report. Enter your email, company name, review your selected layers, add your payment info, and use a promo code in the comments for a 25% discount. Within 20 to 40 minutes, check your email for your beautiful new maps. Take advantage of the promo code below, visit maya-maps.com, and start making your maps today. In this part, I want to show you how you can turn your 2D land cover map into a 3D map by using one very simple trick. And that is, we're going to now create a second map, which is going to be the digital elevation map. And we're going to be using, again, ggplot2 for that purpose. Then we will be having actually two ggplot objects. One is going to be the land cover one, and the other one is going to be the elevation one. We're going to actually place then the elevation map below our land cover map. And then we're going to be using rayshader and extruding that elevation and creating then that 3D layer, and on top having still those land cover classes. Let me show you how we can do that. First of all, we need to turn our digital elevation model raster. We need to turn it into a data frame, just as we did with the land cover raster file. So the first thing you want to do here is, however, we want to reproject our digital elevation model, because remember, this one stayed in WGS 84 coordinates reference system. So we want to use then this proj object for that. And then within the same thing, we were just going to be creating then a data frame with the X, Y, and then the value columns. So we're going to have 3 columns. And we're also going to be getting rid of any missing values that might be there. Finally, we also want to control what is the name of that value column. So I'm just going to call that value column DEM, or just them. Then we can go ahead and actually create our BAM map with the help of ggplot2. Remember, this is the map that we will be putting below our existing land cover map, and then providing it to rayshader and creating a nice 3D map. Now we're going to be doing the same thing with it before. So geom raster, and then over there data is however different. So it will be this one. For the main aesthetics, we're going to be having the same aesthetics. So we're going to be having X, we're going to be having Y, and then for the fill, so we're going to again be using fill, we're going to this time be using them, which is that third value column. Then we want to define here the scale for the fill, but because the values of the digital elevation model are continuous, we cannot use the manual. So in this case, we need to use gradients. So I'm going to be using this scale fill gradient. And then over here, for the colors, and here is the trick, we just gonna choose here white. So essentially this layer is not gonna be visible, but that doesn't matter. It just serves the purpose for us to extrude the elevation in the rayshader itself. So that's kind of the small trick that we're going to be doing here. And then we don't want any legend to show up here. So let's make sure that indeed it's not going to be showing up. So we're going to be disabling here fill for this one. And then what else? Of course, we need to define the coordinates reference system, so everything is in tune. So this one is the one that we also used before, proj. And then what we want to do is, of course, we want to use this. We want to make sure that the legend does not, one which is showing the land cover, right? We don't care about the legend for the elevation. So in this case, we need to add this additional line that legend position is going to actually remove then the legend. And now we can finally render our shader. Main ggplot object in the working with ggplot2 in rayshader is achieved using plot. First thing, what is the GG object? Yeah, in our case, this is. Here comes the trick. Here we can add additional ggplot object, which is going to serve as a layer for creating the height or for creating this elevation, you know, the relief part. So that one is called GG object to use for the height. And in the as in the tutorials that we did, so we can define the width and the height. These are in inches, so I'm going to go 7 by 7. Then this will going to be the window size of. I'm going to go for 600 by 600, and here are pixels, so that's something to keep in mind. Then the next thing is scale. So this is how sharp, so how actually rugged this relief is going to be in the. It's too rugged even for Belgium, which is quite flat when it comes to terrain. So actually, if you have a country, for example, as Switzerland, which is extremely mountainous, you do want to decrease probably this even further. So you should play a bit with this component. We will of course have the shadow, so I'm going to turn it on, but the shadow intensity, so the shadow is going to be quite soft. So the shadow intensity is going to be 1. Then the angle of the scene, I'm going to choose, for example, 87, almost a normal degree angle. I do not want to tilt this around the axis, so I'm going to put that to be 0. And then for zoom, I think I'm going to take some kind of a middle zoom, which is going to be 0.55. And then in case your computer has multiple cores, you can also utilize that by putting here multi-core equals true. So essentially, if you did everything right so far, you should be able to see the scene just like this, what you now see in this upper left corner of your screen. And to render the 3D objects, we can use, again, from rayshader, a package, or actually a function, which is called render high quality. So over here, because we do want to save it locally, we need to define a file name. We can, for example, go for Belgium ESA 3D or a land cover or anything. And very importantly, you need to have an extension here. So I'm going to go for a PNG extension. Then I do want to see as the scene renders. So I'm going to put that as true. Then in terms of the lights, I'm going to place this as false. And then what I actually like to do is I like to take here, because I turned off the light of the main light of the scene, I like to take an environment light. So environment light is the HDRI file, which I like to take from Polyhaven. You probably noticed that also in some of my previous tutorials. So over here, I'm gonna take one, which is called, and I like to use it quite often. It's called Brown Photoshop Studio. It really provides a nice diffuse color or light around the scene. So if you want to actually download this one, don't worry about it. I will include the full code how you can get this one in my GitHub repo. So you can just go there and clone actually the GitHub repo, or just kind of a copy it to your local drive. But for now, I'm just going to indicate this one. You can also find in some of the previous tutorials like how I downloaded this one. And then once you do that, you just need to go ahead and check, what is the intensity you want. One is usually like a default intensity. If you want to decrease, that means the scene is going to be darker. If you want to increase, it's going to be a lighter. So you want to also make sure that is, in tune. And then for the environment, I want this environment light to be kind of a 90 degrees angle. So I want the shadow actually to appear on the other side of the 90 degrees angle if the source of the light is here. Here I do want to try and utilize this different course. So I do want to have here this parallel option turned on. For the width and the height over here, what's very important is that you define here in terms of the pixels. So if you want something like a bit low resolution, you can, let's say, go for 2000, and height also can be 2000 pixels. But remember, you want the ratio that you have defined here in the window size. You also want it here for the width and height. So in our case, they need to be the same. And last but not least, I also like to turn off the interactive option, which allows you to move your scene as it gets rendered, which I find problematic because it often leads to crashes. And here is our final 3D land cover map of Belgium. I'm really happy how this turned out. If you actually zoomed in, you will also see here that there is a relief shade, which gives this 3D vibe. So we successfully turned a 2D map into 3D map. You can also see the shadows in behind, which also, give off this 3D vibe. What I also like is that, the title, the North Star, the scale bar, as well as land cover, they were not really affected. So there was no like shadow adding to them. They're clearly visible. Same goes for the caption. So everything else besides the map stays the same like it was in our 2D map. And this is how you can easily create very effective 2D and 3D land cover maps with ESA Global World Cover data in R using ggplot2 and rayshader packages. I'm really curious how you take this tutorial on a journey across the world and make some of your own awesome 2D and 3D land cover maps. If you're, however, curious how to just replicate today's analysis, I prepared the link in the description box below to my GitHub repo with the code, so do check it out. Feel free to clone it, reuse it, and modify it as you see fit. If you're new to R, you seek to expand your data visualization and geospatial knowledge in R, I prepared a few cool tutorials for you, so do check them out. See you next time.